So today we are going to talk about amplifier circuits a little bit in general and work our way towards an understanding of op amps. So let's call this lecture an introduction to amplifier circuits. So let's say that I have a waveform. So I'll put one over here on the left-hand side. Where this is a function of time, and this graph represents an input signal. That input signal might look something like this. I'm just going to draw a simple sinusoid, or attempt to, apparently. Where this signal could be representative of a voltage waveform or a current waveform. And then over here, on the right-hand side, I'm going to draw yet another waveform. And this is going to represent the output of something. And I might see something like this. Where once again, this waveform could represent a voltage or a current as function. So in order for us to get from this input signal to this output signal, which is just a scaled version of the input signal, so they're both sinusoidal, there might be some phase difference. We'll worry about that kind of stuff when we need to. We really have two distinct options in order to accomplish something like this, in order to scale a signal up. We could use either an amplifier, which is what we are going to be focusing on, or we could use a transformer, which is actually the first topic that's taught in Circuits 3, which you guys will hopefully be taking next fall. So let's talk about what some of the fundamental differences between amplifiers and transformers are, since they can, in some sense, perform a similar role in a circuit or a system. So over here, change that to black, let's put amplifiers. And over here on the right-hand side, let's put transformers. So probably the biggest difference between these two types of devices is that amplifiers are inherently active devices, whereas transformers are inherently passive devices. Does anybody know what the difference between an active device and a passive device is? Or anybody care to venture a guess based on contexts and other things? Patrick?
Some kind of like source has to turn on the active device?
Right, so an active device requires external power, okay? So for a passive device, we've been dealing with passive devices all throughout circuits one, right? So resistors are passive devices, inductors are passive devices, and capacitors are passive devices because they exhibit resistance, capacitance, and inductance, regardless of whether or not they're actually connected to anything. An active device only behaves correctly, so to speak, when it is externally powered. Okay, so that's the biggest principal difference. You need external power for an amplifier to work. You don't for a transformer to work. They literally will always transform or step up and down voltage and current signals. Okay. So there is an interesting result from amplifiers being active devices and transformers being passive devices. Okay. So one of the consequences of this is that the output power of an amplifier, and I want to clarify here what I mean by this is effectively the power that's capable of being delivered to some load, does not have to equal to the input power. Okay. So the output power could be greater than the input power in an amplifier. That's literally what power amplifiers do. Have any of you guys ever heard the term power amplifier before? None of you guys work on, fixing your car stereo or play guitar or anything like that? Power amplifiers provide extra power to drive a large load like a speaker, right? So a speaker is going to convert some voltage signal into sound, but because the speaker has a lot of physical mass, it requires a power amplifier in order to be able to drive that cone and cause it to generate pressure waves, which we interpret as sound, right? So, like I said, in an amplifier, the output power doesn't necessarily have to be the input power, and we can have situations where the output power is greater than the input power because we're taking power from our supplies and applying it elsewhere. In a transformer, though, the output power will always be less than or equal to the input power because it is inherently a passive device. So when the output power is equal to the input power, we have what's called an ideal transformer where there is no power and energy losses whatsoever, but any real transformer is going to have losses because it's made of real things like wires, which heat up when you pass current through them, right? So that's a big fundamental difference between these two things. All right, so now let's divert our focus entirely to amplifiers, okay? So let's talk about what an amplifier is. An amplifier is an electrical circuit or device which increases the magnitude of the signal applied at its input, okay, which is exactly what we observed with this simple graphical example up here. We have a voltage or current signal with a small magnitude, and then through some sort of analog signal processing, it gets converted into a similar sinusoidal signal, but the magnitude is significantly larger, okay? So for right now, let's think of an amplifier as a black box network, okay? So we might have some input terminals over here on the left, and our input signal X of t could be representative of a voltage, a current, or even a power waveform. Then we have a black box that's representing our amplifier. And then over here on the right-hand side, we have our output signal, Y of t, which could be, again, a voltage, a current, or a power waveform. So what the amplifier does is it effectively acts on the input signal X of t to generate an output signal Y of t. And so we can describe this action by its transfer function, where the transfer function A is simply the ratio of the output signal to the input signal. We can write this in a slightly different form. So we could say that our output signal Y of t is simply our transfer function A multiplied by or acting on our input signal X of t. And whenever we're not talking about frequency response, which is something we'll talk about a little bit in this class later on, this transfer function A is more commonly referred to as the gain of the amplifier. Depending on what type of amplifier that we have, this gain may be responsible for converting a current to a current, a voltage to a voltage, a voltage to a current, current to a voltage, or power to power, okay? So there are lots of different types of amplifiers that we might see, and we can, generally speaking, characterize them by their input signal type and their output signal type. So I'm going to make a simple table here. Let's put input in the left column, output in a middle column, and amplifier type over here in this rightmost column. And so let's say that our input signal was a voltage and our output signal was a voltage. Very unsurprisingly, this would mean that we have a voltage amplifier. Voltage amplifiers are the most common type of amplifiers, and we see them literally everywhere. There are multiple voltage amplifiers in our pockets right now because that's an important part of our cell phones, right? So let me explain what I mean by that. How many of you guys have had Physics 202? Almost all of you guys. Great. So because you've had Physics 202, you should roughly know what happens to electric field strength as you get further away from the source. So tell me what roughly happens to the strength of an electric field when you get far away from where it originated. Goes down by a particular factor, distance squared, I believe, right? It's either distance squared or distance cubed. I can't remember. Magnetic field might be distance cubed. Anyway, so the electric field goes down as a function of distance, okay? So that means that, let's say you have your cell phone and you're a long way away from the cell phone tower, okay? the strength of the signal that you're receiving on your phone is very, very small as compared to the strength of the signal that you would receive if you were closer to the cell phone tower. But can you physically hear any difference in the level of the signal or anything like that? No, and it's because there's a simple voltage amplifier that's boosting that signal up to some threshold level, and that's what you hear. That is literally a voltage amplifier. It's also a part of many other types of analog signal processing. You guys are unfortunately going to hear me talk about guitar related stuff a whole hell of a lot because I'm a huge guitar nerd. But all of the preamps that you might see in both solid state and tube amplifiers are all simple voltage amplifiers that do a little bit of wave shaping and all of that kind of good stuff as well. Most effects pedals, or at least distortion and overdrive pedals, are simple voltage amplifiers that have a little bit of extra something in there to cause the sound to be significantly different. But it's just taking a small signal from the output jack of your electric guitar, and that signal is very small because it's just based on electromagnetic induction, and then it's boosting it to a level so that when it goes through the power amplifier stage, which is a secondary stage, it's able to produce enough power to drive a speaker, like we talked about a little while ago, right? So voltage amplifiers are literally all over the place, and that's largely what we're going to focus on in this class. We might also see something where we have current as an input and current as an output, and unsurprisingly, this means that we're dealing with a current amplifier. If we have voltage as an input and take current at the output, we have a transconductance amplifier. If we have current as our input signal and take voltage to be our output signal, we have a transimpedance amplifier. And then lastly, if we have power as our input signal and power as our output signal, we have a power amplifier. So, like I said a moment ago, the most common type of amplifier that we are going to see is a voltage amplifier, and perhaps one of the most common voltage amplifiers that was ever developed is the operational amplifier, or the op-amp. So before we move on from right here, I want to show you guys something. And for those of you that had me for circuits 2, or excuse me, for circuits 1, you've already seen this, but it won't take but a second. If I can get the correct thing to open up. Well, I don't need that stuff or that stuff. Here we go. So this is a functional block diagram of Texas Instruments MUA 741 operational amplifier. It contains just a whole bunch. Don't know why the screen went black. So it contains a whole bunch of bipolar junction transistors. Seems like it says 22 down there, 11 resistors, a diode, and a capacitor. To this point, you guys have used transistors in a few of your freshman classes, diodes in a couple of your freshman classes. you didn't really have any understanding about how they particularly worked, and you're still not going to have any understanding of how those particularly work in this class. We're not going to worry about that too much. What I'm trying to illustrate to you here is that the internal circuitry of a true amplifier is usually pretty darn complex, okay? Now, we don't have to actually worry about understanding how all of that stuff works, because any amplifier can actually be characterized by just three different properties, okay? And those properties are its open loop gain. And we'll talk about what open loop means here in a little bit. Its input resistance and its output resistance. So we can characterize literally any amplifier circuit by those three quantities. And as long as we know what they are, we will have a very good understanding of how it will behave when we connect other external circuit components to it. Well, luckily for us, if we scroll up here in this manufacturer's data sheet, we should be able to find some of that information. Electrical characteristics, here we go, right? So the input resistance for this particular amplifier is typically somewhere in the ballpark of 2 mega ohms. The output resistance for this particular amplifier is usually somewhere in the ballpark of 75 ohms. So that's just ohms, not mega ohms or kilo ohms or anything like that. So there's a huge disparity between the input resistance and the output resistance of this particular op amp and practically every op amp. Here we have the large signal differential voltage amplification. That's just a really fancy way of saying gain. So this is expressed as a typical value of 200 volts per millivolt. So we know that it's a voltage amplifier because the gain has units of effectively volts per volt. 200 volts per millivolt is a fancy way of saying that this particular amplifier has an open loop gain of 200,000, okay? So it has a really, really high open loop gain, a really, really high input resistance, and a pretty small output resistance, okay? That's what we should see for practically all operational amplifier circuits. Some special purpose op amp circuits, like those used in the processing of video, typically have a voltage gain that's only a few thousand, so not hundreds of thousands, potentially millions for other designs. But even though that open loop voltage gain is significantly smaller, we're going to find out that they all work roughly the exact same way. So what we're going to do now is we are going to talk our way through what a voltage amplifier circuit might look like, and then figure out how that model that I talked about a moment ago kind of fits in, okay? So I'm going to put my amplifier here in roughly the middle. And for now, we're still going to just leave it as a black box. Because it's a voltage amplifier, we are going to have some input voltage signal. Let's just say that it's a time varying signal for the sake of argument here. And over here on the right-hand side, we will have our output signal. Also a time varying signal. And I'm going to draw some lines here to kind of separate this portion of the circuit from the others. Okay. So this middle bit right here represents our voltage amplifier. Okay. So now let's focus our attention on the left-hand side, or the input side of things. Okay. So on the input side of things, we are going to have to provide something that's going to give us that input voltage Vn. So could be a current source, but more likely it's going to be some sort of voltage source. So we might have something like this. So this is the signal that I'm trying to amplify, which I'm calling it, which is why I'm calling it Vsig. And our source may have some internal resistance that we need to take into account. So effectively, I'm just representing my input signal source as a practical source. Okay. So everything to the left of the first dashed line is what we're going to consider to be our source side of things. And then we might have some load that we're trying to drive over here on the right-hand side. So the goal, let me write load down here. So the goal in a circuit like this, or what the ideal behavior is that the voltage drop present across our load will be a scaled version of this input signal, Vsig, as a function of time. So we are expecting some sort of behavior such that V load of t is equal to A, the gain of our system, times our signal voltage. Okay. So now what I want us to do is figure out effectively how the amplifier has to work in order to make that happen. And so we're going to do this by effectively just using a Thevenin equivalent circuit, where we're going to look in to the input terminals of the network, figure out what we see, and then we're going to look into the output terminals of the network and figure out what we see. Okay. So if I look in to the input terminals of our network, I'm trying to find a Thevenin equivalent. What do you guys think I might see? So what's a Thevenin equivalent circuit composed of? Let's start there. A voltage source and a resistance. Okay. So I already have a voltage source over here. So I'm probably not going to see another voltage source inside here, at least not when I'm looking in this particular direction. So everything that my signal source sees is going to be just some Thevenin resistance, which I typically call the input resistance of the amplifier, right? So if we redraw our circuit while we're piecing things together, we would have something like this. Sorry, this should be VN. And I'm just going to put a resistance here, Rn, that is representative of the input resistance of our amplifier. Again, we don't actually have to know anything about how it works internally. We just need to be able to determine this input resistance by some means. Okay. If we took this load resistance out and looked into the output terminals, what do you think we would see? Again, we're just looking for a Thevenin equivalent circuit, so probably a voltage source in series with a resistor, okay? Looking in through here, we are going to see some contribution from this signal source, so our Thevenin equivalent circuit will actually include a voltage source. I am going to choose to represent that voltage source as a dependent source in this particular case, okay? And then that dependent source is going to be in series with the output resistance. So that's just the resistance seen looking into the output terminals of a dead network. And then once again over here, I can connect my load. Like so. So let's talk about this guy right here. So we have a dependent source in this case for our Thevenin equivalent circuit, specifically because we know that we want the output voltage of the system to be a scaled version of the input voltage, okay? So that dependent source is going to have a value of what's called AVOL, the open loop voltage gain, times whatever input signal we see across the terminals of our amplifier. Okay. We can see here from this representation that not all of our input signal, or excuse me, our voltage V sig gets applied to the input terminals of our amplifier, because there may be some signal or source resistance that we need to take into account. And not all of the voltage generated here actually gets applied to our load, because our output resistance and our load resistance form effectively a little voltage divider circuit, right? So the output voltage is going to be a scaled version of our signal voltage, but it's going to be influenced by the amplifier itself, the middle section, as well as our signal input resistance and our load resistance. So we have a pretty good understanding now of what's going to go into effectively any voltage amplifier circuit that we could ever have. We can always simplify things down to something like this. And I know this may seem wildly trivial, but it's actually quite true. We can use this for op amps when we get into your later electronics courses and all of that kind of stuff. Using this type of perspective as opposed to doing a whole bunch of nonlinear circuit analysis actually yields the exact same results with a significantly less math. So this simple model, which is called the practical amplifier model, is going to do a lot of heavy lifting in effectively all of the classes that you have where you're dealing with any type of voltage amplification. And we can do simple things like source transformations in order to turn this practical voltage amplifier model into a current amplifier model, or a transconductance amplifier model, or a transresistance amplifier model. They're all basically this exact same setup. But sometimes this resistance is effectively in series as opposed to being in parallel. Sometimes this is a practical current source instead of a practical voltage source. That's the only difference between all of those different types of models. All right, so now, so actually, before we move on here, like I said earlier, we've characterized our amplifier by these three different parameters: our input resistance, our output resistance, and our open loop voltage gain. Okay. So just to be really clear here, the A here stands for gain. The V in the subscript is for voltage, and the OL is for open loop, because we're going to be talking about multiple different types of gains. We might be talking about closed loop voltage gains, things like that. It's important to understand what these subscripts mean. Okay, so this is the practical amplifier model, practical voltage amplifier model. We've spent a good amount of time talking about where it comes from. Now we actually need to make a small change to it in order to use it for an op-amp circuit in particular. So in this particular network, we have a single input signal, V6. But what do we know about op-amps? They have inverting inputs and non-inverting inputs, and we could potentially apply two different input signals to those terminals. So we need to account for the fact that we might have two inputs, whereas this model only gives us access to one, okay? So I'm now going to introduce the practical op-amp model, and it's going to be incredibly similar. So for the next little bit, by that I mean the next week or so, anytime we see an operational amplifier in a schematic diagram, I'm putting the symbol here, right? So this terminal over here to the left is our non-inverting input. This terminal here on the bottom left is our inverting input. And typically speaking, I'm going to call this V plus and this voltage V minus. Over here on the right-hand side, we have our output, which I'll typically denote as V out. And because we know that this device requires external power, I'm going to have a terminal called VCC plus and VCC minus, and those are the terminals that allow me to power this device. So anytime I see this schematic symbol, I'm going to replace it with this network. So here's my input resistance. This terminal will be our non-inverting input terminal. This terminal will be our inverting input terminal. And then over here on the right, I'm going to have the output side that we talked about a moment ago, where I have my open loop gain. And now, instead of having that signal Vn, I'm going to have a voltage Vd that I will define in just a moment, where this voltage Vd is the differential voltage. Okay. That dependent source is in series with our output resistance R out. And then down here at the bottom of the circuit, we are going to have a common ground. Like so. I'm actually going to move this guy. All right, so now let's talk very briefly about our differential voltage VD, which is playing the role of the input voltage in our model that we developed a moment ago. So an operational amplifier in its most basic form is just a very fancy differential amplifier. And all that means is that it amplifies the difference in the input signals. So our differential voltage VD, we are going to define, and it will always be true, is just the potential difference between the voltages applied across our input resistance, where the positive polarity terminal of the differential voltage VD will always be on the non-inverting side of the amplifier, and the negative polarity terminal of the differential voltage VD will always be on the inverting input terminal side of the amplifier. Now, I want you guys to notice something that's very important, and we're going to talk about it here in just a moment. Nowhere on this model does it take into account what our supply voltages are. Okay. Just have that in the back of your mind here while we work a simple example. Okay. So let's say that I want to analyze the following circuit. So I have a simple op-amp circuit where I'm going to apply a 1 volt signal to the non-inverting input terminal. I'm going to ground the inverting input terminal. Let's say that my supply voltages are positive 10 volts and negative 10 volts. And I simply want to figure out what my output voltage is with respect to ground. And let's say that this amplifier is a 741 op amp, like I showed you guys earlier, right? Well, the 741 op amp was characterized by an open loop voltage gain of 200 volts per millivolt, an input resistance of typically around 2 mega ohms, and an output resistance of typically around 75 ohms. Those three values were pulled literally from the data sheet that I showed you earlier. So all I want us to do is just figure out what the output voltage of this system is going to be. So I'm going to start my analysis by replacing the op amp portion with the practical op amp model. So here's my 2 mega ohms input resistance. Um, 200 volts per millivolt is 200,000. So I'm going to choose to represent that as 2 times 10 to the 5. Where this will be our voltage VD. $75 ohm resistance is our output resistance. And then here's the output voltage that we're looking for. So that's my practical op-amp model. Now I'm just going to make any external connections that I can, okay? So for instance, I can see that my inverting input terminal, which is always associated with the negative polarity terminal of VD, is tied to ground. So I can simply connect this node to ground like so. On the non-inverting input terminal side of things, I can see that I have a 1 volt source between the non-inverting input terminal and ground. So I could put a 1 volt source here. I don't have any load connected, so there shouldn't be a resistive path between or across the output terminals of my device like so. So this looks pretty correct to me, okay? Before we move on to the analysis, does anybody have any problems with how I drew things here? All I did is replace the 741 op-amp part with the practical op-amp model, and then I just made my external connections that were appropriate. Putting in circuit elements when I needed to, wires when I needed to, all of that kind of good stuff. So if we're all on board with that, let me ask you guys a question. Okay. Effectively just by inspection here, and I'm not looking for a number to be clear, at least not yet. What should my output voltage be? Or what's the voltage drop that I'm going to see across this open circuited set of terminals? So it will be exactly what's provided by the dependent voltage source, right? I know that because this is open circuited, there's no voltage drop across my 5 ohm resistor because there's not any current flowing through it. So whatever voltage I have here is the voltage at my output terminals. Absolutely correct. So I can put this as 2 times 10 to the 5 times whatever VD is. So that begs the question, what's our differential voltage VD? Yeah, so just 1 volt, right? So the positive polarity terminal of VD is at the non-inverting input node. The positive polarity terminal of the 1 source is at the non-inverting input node. The negative polarity terminal of VD is at the inverting input node, which is tied to ground. The negative polarity terminal of the 1 volt source is also tied to ground. So VD is literally just the 1 volt that we are applying between the input terminals. So now, I want a numerical answer for what V out is. Yes, so 200,000 volts. Now, everybody okay with that? Literally just simple substitution. That's what our model tells us, but does that make any practical sense whatsoever? If I went upstairs in my office and got 741 op amp out of one of my little kits, and I hooked up the op amps to positive 10 and negative 10 volt supply voltages, and then applied 1 volt across my device, would I get 200,000 volts at my output? What do you guys think? No. Okay. These aren't magic devices that allow us to generate incredibly large voltages by any stretch of the imagination. They have limitations. Okay? The limitation on the output voltage of an operational amplifier is, loosely speaking, whatever our supply voltages are. Okay? Now, technically speaking, that's only true for what are called rail-to-rail op amps, meaning that their output voltage range goes all the way up to VCC plus and all the way down to VCC minus. There are many op amps that don't operate in a rail-to-rail configuration, and so typically there's between 3/4 of a volt and 1 volt of difference. I'm not going to worry about that. We're going to assume every op amp in this class is a rail-to-rail op amp, just so that we can say that the constraints on our output voltage signal will always be VCC plus and VCC minus. Okay. So we call this concept saturation distortion. So in any real op amp circuit, the output voltage cannot exceed the power supply voltages. I'm going to give you guys a mathematical relationship here in just a moment, but I want to talk about what saturation means. So in the context of electrical engineering, what saturation typically means is that a change in the input signal does not cause a subsequent change in the output signal. So we can keep driving the input signal up, but the output will never exceed that 10 volts. So we say that the output is saturated to the supply voltage. Okay? So mathematically, this can be represented like so. The output voltage, V out, will be equal to the positive supply voltage, VCC plus, whenever our open loop voltage gain times our differential voltage, which I'm representing here as V plus minus V minus, is greater than or equal to VCC plus. And we call this positive saturation. On the other side of things, our output voltage will be equal to VCC minus whenever the product of our open loop voltage gain and our differential voltage is effectively more negative than VCC minus. We call this negative saturation. And then in the middle, our output voltage will be equal to our open loop voltage gain times our differential voltage whenever VCC minus is less than our open loop voltage gain times our differential voltage. And that needs to be less than VCC plus. And in this, what we're going to find in a moment, very narrow region is where we get linear amplification. So we have linear operation, meaning that our output voltage is a scaled version of our input voltage, which is how we expect the amplifier to actually behave. Okay. So it should be fairly easy to understand that the larger this open loop voltage gain is, the smaller this window for linear operation is, right? So the mu 741 op amp, which has an open loop gain of 200,000, should ostensibly have an incredibly small linear range of input signals that it can actually amplify. Okay? So the linear range of an amplifier can be defined like so. So we simply take our negative supply voltage, VCC minus, divide it by the open loop gain, and that shows us effectively the smallest signal that we could possibly amplify. And then VCC plus divided by our open loop gain tells us the largest signal that we could possibly amplify. And so all of our allowable input voltages are between those two extremes. Okay. So for our 741 op amp in the previous example, let's figure out what that linear range would actually be, right? So our supply voltage was negative 10 volts. Our gain was 2 times 10 to the 5. And then on the other side, our positive supply voltage was positive 10 volts. And our gain was once again 2 times 10 to the 5. So let me grab a calculator real quick. So negative 10 divided by 2 times 10 to the 5. Let me divide that by 1 times 10 to the minus 6, so that I can put it in terms of microvolts. So this is effectively negative 50 microvolts, positive 50 microvolts. So this is the range of input signals that my 741 op amp should be able to linearly amplify. Okay. So the overwhelming majority of voltages fall outside of that linear range. So that means that in an open loop configuration, the operational amplifier, as we understand it, actually does a pretty terrible job as an amplifier because it can only amplify signals where, and what I mean specifically by amplification here is the output signal is a scaled version of the input signal. Whenever the input signal is between plus and minus 50 microvolts. Okay. Now, there are some very specific applications where this incredibly small linear range is useful. And so that's what we're going to talk about in our next class meeting. Okay. So our next class meeting is going to be dedicated to looking at different circuit topologies that satisfy an open loop op-amp configuration. We're going to talk about how they're used in specific instances, and then we're actually going to design a very simple analog to digital converter using an open loop amplifier. So we're going to start designing stuff literally third day of class. All right, so that is enough out of me for today. So I'll see you guys on Monday morning for more op-amp brutality.